For section 4.5, let's talk about LHospitals Rule. Now, LHospitals Rule is a method to find the indeterminate limits. We've seen limit problems in earlier sections, and this is just going to give us one more useful tool in order to evaluate them, and it's actually the best tool. So let's just go back and think about how we did limits back in Chapter 2. So I said we've solved limits algebraically. If I gave you some simplistic function like the limit as x approaches 1 of x squared minus x over x squared minus 1. Now, you know you can't simply just plug the 1 in because your numerator would be 0 and your denominator would be 0. And you say, well, I can't answer what 0 over 0 is. It's an indeterminate limit. Now, keep in mind, yes, it means that this function is undefined at 1. That doesn't mean that the limit does not exist as x approaches 1. So what we had to do when we solved these limits algebraically is you could factor the numerator and denominator. And every single time the limit existed, I said that there had to be an algebraic simplification. So the factor that causes the denominator to equal 0 ends up canceling with the same factor in the numerator, and you're left with the limit as x approaches 1 of x over x plus 1. Then you can say, well, now at that point you can evaluate the limit. If you plug a 1 into this function, you'll get your 1 over 2. And remember what that means. We're not saying the function exists at 1, but we're saying you can get as close to 1 as you want, and the y values are going to get as close to 1/2. So even though it doesn't exist at 1, it exists at 0.1,000,000,000, or it exists at 1.0000000000001. So we need to know what the limiting value is, even if it doesn't exist at 1. Now, on the other hand, we also used logic whenever we had infinite limits, and I'll say we also used algebra in those. Now, if I have a limit as x approaches infinity of an expression like 2x squared minus 1 over 5x squared plus 1, this is back in section 2.7 in your book. The topics of that section told us in order to simplify this expression, you divide by the degree of x in the denominator. So I go through and I divide everything in this equation by an x to the second. Then I simplify algebraically and I say, well, this is the same thing as the limit of 2 minus 1 over x squared divided by 5 plus 1 over x squared. Then you take the limit. And you know any finite number divided by an infinite number becomes 0. So your numerator becomes 2 minus 0. Your denominator becomes 5 plus 0. Clearly we just get our 2/5 in that case. Now with these infinite limits, remember I also told you anytime you have the degree of the numerator and denominator that match, your limit's just going to be at the fraction of the leading coefficients, which of course this one proved was true in this case. Now, what these two types of limit solutions algebraically cannot handle is what we're doing now. So I say, however, till now, we couldn't evaluate the limit as x approaches 1 of the natural log of x over x minus 1. There is no algebraic simplification to that. Now that does not mean that the limit doesn't exist, it's just algebra can't show it. So LHospitals Rule is something that's going to become very necessary and very useful. LHospitals Rule states that if a limit as x approaches a of f of x over g of x is of indeterminate form. What do I mean by indeterminate form? Just like you saw up here. This one was 0 over 0 when you tried to plug in the 1. This one would have been infinity over infinity when you tried to plug in the infinity. Both of those are called indeterminate forms. They may or may not have an answer to the limit. Well, what this says is that anytime it's of indeterminate form, then the limit as x approaches a of f of x over g of x is going to equal the limit as x approaches a of the derivative of f of x over the derivative of g of x. And then I put, please note, it's not the quotient rule. All you're doing is taking the derivative of the numerator, dividing it by the derivative of the denominator. Now, you'll also notice I put a little h over the equal sign. We typically do this whenever we use LHospitals Rule because from this step to this step, it does not follow through algebra or anything else as we're normally seeing equations where you say, well, this side of the equation is equal to that side of the equation. That's not true in this case. So this does not equal that, but their limits do equal according to L'Hopital's rule. And that's why we put the h over the equal sign. We say, yeah, okay. L'Hopital's rule says that we can take the derivative of the numerator over the derivative of the denominator. This is just showing the reader of the problem that that's what you're doing in this step. Now, to see this in action, some examples I have here. Well, the first example, I have the limit as x is approaching 1 of the natural log of x over x minus 1. Well, okay, that's the problem I talked about. We could not solve algebraically up here. If I tried to plug the 1 in, your numerator natural log of 1 is 0. Your denominator 1 minus 1 is 0. This is of indeterminate form 0 over 0. So L'Hopital's rule says, okay, just go ahead and take the derivative of the numerator, 1 over x, over the derivative of the denominator, derivative of x is 1. So I can say this limit simplifies down to here. Now you'll notice, whenever I take the derivative of the numerator and derivative of the denominator, I must put an h over the equal sign. From this step to this step, I'm merely just simplifying, so I don't put the h over the equal sign. I say this is just equal to the limit of 1 over x, which we know as x approaches 1 is just 1 over 1. We get our limiting value of 1. Now, for the next problem here, I have the limit as x approaches 0 of 3x minus the sine of x over x. If x is 0, your numerator is 3 times 0 minus the sine of 0. All that's 0. Your denominator is 0. Yet again, it's of the indeterminate form 0 over 0. So L'Hopital says you should be able to use this method of taking the derivative of the numerator over the derivative of the denominator and then evaluating your limit. So I do that. Derivative of my numerator is 3 and then minus cosine x. Derivative of the denominator x gave me a 1. So now I have the limit as x approaches 0 of 3 minus cosine x over 1. When I try to plug a 0 into that, my only x is in the cosine function. Cosine of 0 is 1. My numerator becomes 3 minus 1 over a denominator of 1. Simplifies to give me a 2. So I can say so far these are working pretty straightforward. One use of L'Hopital and everything's gorgeous. Well, look at the third one here. It's going to remain the same for now. If I take the limit as x approaches 0 of the sine of x over x plus x squared, I can see L'Hopital is necessary because when you try to plug a 0 in the numerator, sine of 0 is 0. Any polynomial that doesn't have a constant clearly is going to be 0 when you try to plug a 0 in. So L'Hopital says your numerator now is going to be the cosine of x and your denominator is going to be 1 plus 2x. The instant I get that 1 in the denominator, I know I'm done because it's no longer going to be 0. So your denominator, once you plug in x is 0, becomes 1 plus 2 times 0. Your numerator, cosine of 0 is 1. We get our 1 over 1 for our answer of 1 again. Now, for number 4 here, you can already see I've had to use L'Hopital several times, and that's something you'll want to keep in mind. There's no limit to the number of times L'Hopital can be used. Most problems, once or twice is enough to solve it out. Sometimes it'll require more than that. So when I look at this one, I can say, well, if I try to plug 0 in the original equation, I would get 0 minus the sine of 0. Numerator is 0. Your denominator would be 0 cubed. 0 over 0 is indeterminate. So I use L'Hopital. Derivative of x is 1. Derivative of sine of x is cosine x. So I have 1 minus cosine. Your denominator becomes 3x squared. Well, notice when you try to plug a 0 in, clearly your denominator is still 0. Your numerator would be 1 minus 1, which is also 0. This is still indeterminate in this format. So I use L'Hopital again. Derivative of the denominator, 3x squared becomes 6x. Derivative of 1 cancels out in your numerator. Then you say, well, the derivative of negative cosine is positive sine. So now I look at this fraction and say, can I evaluate it now? No. Sine of 0 is 0. 6 times 0 is 0. So it's still indeterminate. I use L'Hopital one last time, and I know this time is the last time, not because I see it on my sheet, because I see what the denominator is. Derivative of 6x is 6. The very instant you get a numerator or denominator other than 0, you're done. So my denominator is 6. My numerator, derivative of sine, was cosine, and I know that the cosine of 0 is 1. So now when I evaluate this last fraction at 0, you'll just get 1/6 for your final answer to the problem. So we know that the limit as x approaches 0 of x minus the sine of x over x cubed is 1/6. Pretty cool how L'Hopital can simplify that out. Now, I know what you're thinking. You're thinking you want to see some more difficult L'Hopital's problems. So do I. What if we have some with exponential functions in there? And let's look at a limit as x is approaching infinity in this case. So if I say, well, the limit as x approaches infinity of e to the x over x cubed. Try to plug infinity into that. E to the infinity, clearly that's an infinite number. Infinity cubed, that's an infinite number too. Turns out that the numerator is way larger than the denominator, though. This answer is going to be an infinity, and we can see that by using L'Hopital pretty easily. Notice, infinity over infinity, that's one of our indeterminate forms that we talked about on the preceding page, so L'Hopital should be able to help. Well, when I try to use L'Hopital, I say, well, it's just the derivative of the numerator over the derivative of the denominator, and instantly I already know what the answer is, and you should too. Look what's going to happen each time you take the derivative of the denominator. That polynomial is going to be losing power. What happens to the exponential function in the numerator? Nothing. Derivative of any exponential function is that exponential function. So I can see that that infinity, it's not going away in the numerator. However, it will eventually go away in the denominator. Technically, in this step, it's still infinity over infinity. So I would take the derivative again and get e to the x over 6x. That's e to the infinity over 6 times infinity, still infinity over infinity. So I would use L'Hopital again and say, well, your numerator's not going anywhere. But now, after 3 uses of L'Hopital, your denominator's just a 6. The instant you get a finite number in part of your fraction, you're done. Because now you can say, can I evaluate at an infinity? Sure. Your numerator e to the infinite power is an infinite number. Your denominator is 6. Infinity divided by any finite number is infinity. So we don't ever say infinity over 6 for the final answer. We just say it's an infinite number. Now, for the next one here, if I say I want to evaluate this expression as x approaches 0. So when I'm thinking about as x approaches 0, this would become the square root of 1 minus 1, then minus 0. So your numerator is 1 minus 1, 0. Your denominator would be 0 squared. 0 divided by 0 is one of the forms L'Hopital should be able to handle. So I took the derivative of that square root. I know it's just the group to the 1/2 power. Its derivative is going to be 1/2 times the group to the negative 1/2 times the derivative of the inside, but that's just a 1. Then the derivative of the constant went away. Derivative of minus 1/2 x became minus 1/2. Derivative of the denominator, 2x. Now at this point I was thinking, okay, can I plug the 0 in now? No. The reason you can't is because you would have 1/2 times the group 1 plus 0, so that's just 1/2 times 1, minus 1/2. Your numerator is 0, your denominator is 2 times 0, it's 0. So I used L'Hopital again, since this is still in the format 0 over 0. When I used L'Hopital the second time, this group, the negative 1/2, came down in front, gave me a negative 1/4, times the group 1 plus x to the negative 3 over 2. Derivative of the constant went away. Derivative of 2x in the denominator is 2. And so now if you plug in a 0 for x, you're just going to have 1 plus 0 to the negative 3 over 2. We both know 1 to any power is 1, so your whole numerator is just negative 1/4 times 1. It's a negative 1/4. Divide that by the denominator of 2, and you'll get your negative 1/8 for the final answer there. So that's a pretty cool problem. The next one, and this is our first one we've seen, where you're going to really have to think about whether L'Hopital should be used or not. So when I go into the original problem, it should be used here. Why? I'm giving you the limit as x approaches 0 from the left of the sine of x over x squared. Well, sine of 0 is 0. 0 squared is 0. In the original format, it is 0 over 0, which is one of our indeterminate forms. So I use L'Hopital, which says I'm going to take this same limit, evaluate it at the derivative of the numerator over the derivative of the denominator. But then as soon as I do that, I can say, well, I'm done with this problem. Why am I done with this problem? The very instant you no longer get a 0 in your numerator or denominator, L'Hopital can't help anymore. So I know that if I evaluate the cosine at 0, it's going to give me a 1. I have to stop. So I say, well, cosine evaluated at 0 is 1. My denominator is going to be 2 times an infinitesimally small negative number. That's what I tried to show here. So 1 divided by 2 times an infinitesimally small negative number, well, 2 times an infinitesimally small negative, it's still going to be an infinitesimally small negative number. 1 divided by an infinitesimally small number is infinity, but this is a positive divided by a negative, so I get a negative infinity. Now, all of the problems we've looked at so far have been where the original problem was in fractional form, whether it's 1, 2, 3, 4, or 5, 6, 7. I gave you fractions for all of them. It's not always going to be in that format. So notice now I'm saying, well, what if instead of a fraction in the original problem, you're given a product? So I have some number approaching positive or negative infinity times a number approaching 0. So I said, well, these are also able to be solved with L'Hospital's rule. The way we go about doing it, let's say I gave you a problem like the limit as x approaches negative infinity of x times e to the x. Now, if I think about what this is when I plug it in, clearly the number out in front that I'm multiplying, that's approaching negative infinity. But then e raised to the negative infinity, that means 1 over e to the infinity. Well, 1 over e to the infinity would be a number approaching 0. So I have a number approaching negative infinity times a number approaching 0. This tells me that L'Hopital should be able to handle it. But for L'Hopital to work, I have to force whatever I have into a fraction, because L'Hopital is specifically the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of the numerator over the derivative of the denominator. So even if you're not given a fraction in the original problem, you have to form a fraction. So you'll see this original problem that I did here, I went ahead and said, well, let's let that x stay in the numerator. I can force that e to the x to the denominator by calling it e to the negative x. And so now I can use L'Hopital by saying derivative of the numerator over the derivative of the denominator. Derivative of x is 1. Derivative of e to the negative x is e to the negative x times the derivative of the exponent, which is what gave me the negative 1 out in front. So now I can go ahead and evaluate this at our value of negative infinity by saying, well, okay, the numerator is already a 1. The denominator, if I plug in a negative infinity for x, keep in mind this is going to be the negative of negative infinity. So you said, well, that's e to the infinity down there in that denominator, which is going to be an infinite number, but then you have the negative out in front of it. So you say, well, it's just 1 divided by negative infinity. Well, any finite number divided by any infinite number is 0. Should I say a negative 0? No, absolutely not. Not for the final limiting value. So is it approaching 0 from values below 0? Absolutely. But the number it's approaching is 0. You can think of this as something like 1 divided by negative a whole bunch of 9s, and you just say, well, that number is approaching 0. My calculator had to put it in scientific notation, it's so small. Yes, it is slightly negative, but the limiting value is 0. Now, up next, for number 9, give you a similar looking problem, except now instead of an exponential, I have a trigonometric function in there. So I have the limit as x approaches positive infinity of x times the sine of 1 over x. So I know this number is approaching infinity. This number is approaching the sine of 0, which is 0. So I need to simplify this out. It's one of these indeterminate products. This time I'm choosing to leave the sign in the numerator. I move this x down to the denominator by saying, well, if you have a factor of x in the numerator, then you have a factor of 1 over x in the denominator. And then I knew that that was going to work out nicely because when I take the derivative of the numerator, the chain rule derivative of the inside is just going to cancel with the derivative of the denominator. And that's going to be beautiful. To see that in action here, I went ahead and said, okay, I'm going to use L'Hopital. Derivative of the numerator. Derivative of sine is cosine. I keep the angle times the derivative of the angle. Now, where I got that from, I thought of that angle as x to the negative 1 power. The derivative of x to the negative 1 would be negative 1 x to the negative 2, which is negative 1 over x squared. Same thing in the denominator. Derivative of x to the negative 1 is negative 1 times x to the negative 2, or negative 1 over x squared. Clearly, those cancel in this step, and I can say, well, this is just equal to the limit as x approaches infinity of the cosine of 1 over x. That becomes the cosine of 0, and the cosine of 0 is 1. The next of our indeterminate forms, so we had problems that are already fractions, problems that are products to begin with. Well, what if I have an infinite number minus another infinite number? As we've already seen, some infinite numbers are larger than other infinite numbers. In fact, the infinite number you get from e to the infinity is infinitely times larger than the infinite number you'd get from, say, an infinity cubed. So there are certainly different sizes of infinity. So I'll say in this problem, if I'm looking at the limit as x approaches 1 from the right, 1 over the natural log of x. We know the natural log of 1 is 0, so this is 1 over 0, which is going to be an infinite number, minus, and that's, I shouldn't say 1 over 0, I should say 1 over a number approaching 0 from the right, which is infinity. And your next one, if you have 1 over a number slightly larger than 1, minus 1, that's again approaching 1 over a number slightly greater than 0, which is going to go to infinity. So now, in order to solve this, I went ahead and got a common denominator. In order to get that common denominator, I had to multiply the first fraction by x minus 1 over x minus 1. That's where this numerator of x minus 1 came from, over that common denominator. And then I said I had to subtract the second group, and in that second group I had to multiply it by the natural log of x over the natural log of x. That's where that minus natural log of x came from in the numerator, over our common denominator. Now from this step to the next, I had to use L'Hopital. Derivative of the numerator gave me 1 minus 1 over x. Derivative of the denominator, derivative of the natural log of x is 1 over x. That's the derivative of the first times the second, plus the first, the natural log of x, times the derivative of the second, which is just your 1. So then, guys, what I did after that was I said I'm going to keep that numerator of 1 minus 1 over x, and I'll simplify my denominator. I'm going to distribute that 1 over x throughout that group, and when I do, I'm going to get 1 minus 1 over x plus the natural log of x. Now please be careful. Those 1 minus 1 over x's don't cancel because it's not a factor in the denominator. So I said, well, all right, from that step, can I go ahead and evaluate? And unfortunately, no, because you still have 1 minus 1 in your numerator, so that is indeterminate. So I went down and I used L'Hopital again. I needed to show that, so I need to put an h over the equal sign there. From this step to this step, I'm using L'Hopital. I said derivative of 1 is just 0. This is the same thing as negative x to the negative 1. The derivative of negative x to the negative 1 is going to be positive x, or positive 1 x to the negative 2. That's where you see the 1 over x squared come from. Same thing in the denominator. This is going to give me a positive 1 over x squared. Derivative of the natural log of x is 1 over x. At that point you say, can we evaluate? Absolutely. You can easily plug in a 1 now. Your numerator is going to be 1. Your denominator is going to be 1 plus 1. We get our final limiting answer of 1/2. Now, the last few problems in this section, and this is a glorious section, I want to do one more of these where we take an infinite number minus an infinite number. Notice in this one I'm saying take the limit as x approaches 0 of the cosecant x minus the cotangent of x. I went ahead and thought about it like this and said, well, cosecant's just 1 over sine, cotangent's cosine over sine. If I'm thinking about this, it's going to be 1 over 0 minus 1 over 0. That's going to be an infinite number minus an infinite number, since when I say 1 over 0, that denominator is just a number approaching 0. We know 1 over 0 is undefined, but not when the limit is just approaching 0. That's going to be an infinite number minus an infinite number. So I need to try to simplify that. Just like the last problem, I'll get that common denominator, which these already have, of sine of x. My numerator becomes 1 minus the cosine. So now when I tried to evaluate this, you'd say, well, you can't right now because your numerator would be 1 minus 1, which is 0. Your denominator would be 0. So that's indeterminate. L'Hopital can help, though. So L'Hopital says take the derivative of the numerator. Derivative of negative cosine is a positive sine. Derivative of sine is cosine. So you can say, well, at this point, you're done because that denominator we know is a 1. As soon as part of your fraction is no longer 0, you're done. So I tried to evaluate. Sine of 0 is 0. Cosine of 0 is 1. Well, 0 over 1 gives me a definitive answer of 0. Now, our last format of problems that we're going to look at is when we have forms of exponential functions. What if you have an exponential base 1? We always know 1 raised to any power is 1. Well, what if the base is just a number approaching 1 raised to a power approaching infinity? So what is 1.000000001 raised to an infinite power? Well, we're going to have to think about that. That's indeterminate. And we always say 0 raised to any power is 0, but then we have another rule that says any number raised to the 0 power is 1. So what is a limit when the base is 0 and the power is 0? Well, that's indeterminate. What if the base is approaching an infinite number and your power is approaching 0? We say, well, infinity raised to any power is infinity, but then we say any number raised to the 0 power is 1. So you have conflicting rules. So we have to think about what happens when we put inside of a limit and these two numbers are approaching those values. Now, the way that all of these are done is by using logarithms, because the initial problem is not going to be something that you can put into fractional form. So you're going to have to force the quotients by using logarithms. Let me show you what I mean by this example right here. We have the limit of the exponential base 1 plus 1 over x, and then that's raised to the x power. So if I'm thinking about what happens as x approaches infinity, notice this is going to become 1 plus 1 over infinity. So in other words, it's 1 plus a number approaching 0. So your exponential base is a number approaching 1. But then your exponent is certainly approaching infinity. So this is the first scenario there. Your base is approaching 1. Your exponent is approaching infinity. So what is the limit of this base approaching 1 raised to an exponent approaching infinity? What I'll go in and do to try to handle this is I'm going to say, let's let f of x equal the limit of whatever you're trying to, or let's let f of x equal the function you're trying to take the limit of. So first I do that. Now, in order to get a fraction, I'm going to use logarithmic differentiation here. I'm going to just say, let's take the natural log of both sides of this expression. So notice, the natural log of f of x is going to equal the natural log of the right-hand side, this group 1 plus 1 over x to the x. You know the advantage of that is now any exponent on the term inside of a logarithm can come down in front. That's what I did. But then I also remember L'Hopital requires a fraction. So once I get a product, it's easy to create a fraction. I'll just leave the natural log in the numerator and then make my denominator, if this is multiplying by x, that's the same thing as dividing by 1 over x. So then I can say, well, the limit as x approaches infinity of the natural log of f of x. Now I know this is not going to take me directly to my answer, but I have to find this one first. I would like to find the limit as x approaches infinity of f of x. That's my original function, but I can't. I'll say, well, instead, I'll go ahead and find the limit as x approaches infinity of the natural log of f of x, and it's going to equal the limit as x approaches infinity of this expression. Clearly, when I try to plug in an infinity, I'd get the natural log of 1, which is 0 in the numerator. 1 over infinity would give me a 0 in the denominator. So I use L'Hopital to try to simplify it out. When I do that, I know that the derivative of the numerator, derivative of any logarithmic expression, is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. The derivative of 1 over x is negative 1 over x squared. But notice that same derivative becomes our denominator. Derivative of 1 over x is negative 1 over x squared. Well, those negative 1 over x squareds cancel in this step, and I can say this is just the limit as x approaches infinity of 1 over 1 plus 1 over x. And then I can say, well, I can evaluate that. Let x go to infinity. Any finite number divided by an infinite number goes to 0. This becomes 1 over 1 plus 0, which is just 1. So now I can say, then the limit as x approaches infinity of the natural log of f of x clearly is equal to that 1. That wasn't what we wanted, though. We wanted to know what's the limit as x approaches infinity of f of x. And what I've done from this step to this step, guys, is I just said, well, in order to get rid of that in order to get rid of that logarithmic function, all I've done is I've exponentiated with exponential base e on both sides. If I put this side into the exponent of an e and natural log eliminate each other, and I just have f of x. Put the right-hand side inside of an exponent of an e, and you've got e to the first power. So I can say the limit as x approaches infinity of f of x is simply e. Therefore, the limit of my original problem, which I let f of x equal, is also equal to e. Gorgeous. Now, that's a wonderful problem, and you won't see many that use this property where you have to take the logarithm of both sides. One last problem I wanted to show, just because inverse trig functions are cool and sometimes students forget their derivatives, and you can never forget your derivative of these functions. If I gave you something like the limit as x approaches 0 of the inverse tangent of x divided by the inverse sine of x. Well, if you think about this, the inverse tangent of x, it's asking you, when is the tangent function 0? Well, that's at 0. And the inverse sine of x, well, if x is 0, it's asking when is the sine function 0, and that's at 0. So right now, this is 0 over 0, which is indeterminate. So I use L'Hopital. Derivative of the inverse tangent is 1 over 1 plus x squared. Derivative of the inverse sine is 1 over the square root of 1 minus x squared. So then I just said, well, if you're dividing by a fraction, that's the same thing as multiplying by the reciprocal of that fraction. So this square root of 1 minus x squared is actually going to go into the numerator whenever I algebraically simplify this. And I have the square root of 1 minus x squared over 1 plus x squared inside this limit as x approaches 0. And at that point, there's no reason to not go ahead and evaluate the limit. Allow x to go to 0. Your numerator becomes the square root of 1. Your denominator is 1. And you know the square root of 1 over 1 is 1. And you're like, wow, that's a pretty cool problem. Hopefully. And I think you'll see that L'Hopital's rule is a fairly straightforward technique. It is a technique that you are never going to get away from in the rest of your calculus classes. L'Hopital's rule is something you absolutely need to know. So please let me know if you have any trouble with the problems in this section. We need to make sure that you grasp this concept very well. And its base point principles, it's fairly simple. If you have a fraction that you can't take the limit of because it's going to 0 over 0 or infinity over infinity, you just take the derivative of the numerator, divide it by the derivative of the denominator, and then try to evaluate again. And you keep on doing that until you get something that you can evaluate. Please let me know if you have any questions in this section. I'd be glad to help.